7-4 Matrices and Systems of Equations. In this section, we'll learn another way of solving systems of equations, systems specifically of linear equations, like you had learned in Algebra 2. This way is going to be using something called a matrix. So a matrix is really just a rectangular array of real numbers. When we have more than one matrix, we call it matrices. So if m and n are positive integers, then an m by n, so we read that as almost like if you were to go to Home Depot and get a 2x4, it's an m by n matrix as a rectangular array. So we see this one here where we have different numbers, and it's really just drawn in this nice rectangular form. A sub ij is considered an entry, and what that means is it is in row I and column J. Almost like if you were to open an Excel document and you have your rows and your columns. Okay. An m by n matrix has m rows and n columns. So the first number here is my my rows, and my second number here is my columns. So this is rows, this is columns. Okay, so a matrix that has m rows and n columns is said to have dimension m by n. And if m and n are equal to each other, that means it is a square matrix. So it would be 2 by 2 or 3 by 3 or 4 by 4. And then the entries in a square matrix that go on a diagonal are considered the mean diagonal entries. So we want to just determine what is the size, the dimension of each matrix. Remember, it's row by column. Okay, so here there's only one row and one column, so we say this is a 1 by 1. Here we have one row, but 1, 2, 3, 4 columns, so this is a 1 by 4. In the next one, we see we have 2 rows and 2 columns, so we say it's a 2 by 2. We have 3 rows and 2 columns, so this is a 3 by 2. And lastly, 3 rows, but only 1 column, so it's a 3 by 1. We can have a bunch of different types of matrices. Here we can have a row matrix, which has only one row, just like in example B. The column matrix, which is just only one column, that would be like part E here in the end. An augmented matrix, which is the next thing we're going to talk about, takes a system of linear equations and puts it into a matrix form. So let's see what that looks like. Here we have a system of linear equations. X minus 4y plus 3z equals 5. Negative x plus 3y minus z equals negative 3. And 2x minus 4z is equal to 6. We have everything nice and lined up like we would do in algebra with elimination. What we're going to do is anywhere there is an empty spot, we're going to throw in a 0. Okay. So what we can do with an augmented matrix is we're going to drop the letters and we're only going to use the numbers here. Don't forget, anywhere we don't see a number, there is technically a 1 in its place. All right, so our augmented matrix almost looks identical here. We're just going to put gaps. So we have 1, negative 4, 3, and that is equal to, so we're going to put 3 vertical dots, 5. We're going to do the same thing for the rest. Negative 1, 3, negative 1, that comes from the coefficients, and dot, 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 negative 3. And then we have 2, 0, negative 4, dot, 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 6. All right. We also have something called the coefficient matrix. The coefficient matrix is literally just the coefficients. So just the numbers in front of the variables. That's 1, negative 4, 3, negative 1, 3, negative 1, and 2, 0, negative 4. The constant matrix is exactly what it sounds like. It's just the constants, so just the numbers without variables. So that's these guys over here, 5, negative 3, and 6. All right, so we can write an augmented matrix just by, well, doing exactly what we just did there. We are going to make sure everything is nice and lined up first, though. So here we see we have variables x, y, and z. We want to make sure everything's nice and spaced out. So we have x plus 3y. We'll leave a gap for the z. Negative y plus 4z is equal to negative 2. And we have x minus 5z is equal to 0. And anywhere with an empty spot, we're going to put in a 0 for it. And anything that didn't have the number written, but the variable was there, we're just going to throw in the 1 so we don't forget. All right, so our augmented matrix is just going to take all of those digits. So we have 1, 3, 0, ... 9 because it's equal to 9. 0, -1, 4, again, ... -2, and then 1, 0, -5, ... 0. And there is our augmented matrix. Now we also can perform something called row operations. And this is basically taking a strategy that we would have used to solve the system and using it to help us solve the system using a matrix instead. So we're allowed to do a few things. First of all, we're allowed to rearrange the rows. So I can make row 1 turn into row 2. I can just switch which spot they're in as long as I keep the numbers that are in line together in line. So I can just switch. So if I wanted to put this in the second row, I could do that. It doesn't matter. And then put this in the first row. Makes no difference. Okay. So for now, what we would normally do if we were to start to perform some operations is we would label these. We would call this row 1, this row 2, and this row 3. We don't need to label the columns because things are going to happen in rows because they are row operations. So we can switch rows around. We can multiply rows by some sort of constant, just can't be 0, otherwise it cancels it all out. Or we can take a multiple of a row and add it to another row, which is essentially how we do elimination in, think back to like algebra 1, right? We multiply one of the system or the equations in the system by a number, and then we start canceling some stuff out. All right, so two matrices are considered row equivalent when one can be obtained from the other by a sequence of elementary row operations. So what we're going to end up trying to do is to simplify these, and you'll see kind of how, into row equivalent matrices. Okay, and then when it is more simplified, we'll be able to easily pick out that x equals this number, y is this, and z is this. So first, let's just practice some of our options here. So we have our original matrix. This isn't augmented, it's just a regular matrix. Doesn't matter, it all works the same. And we want to interchange the first and the second rows. So this is row 1, this is row 2, this is row 3. I want to switch the rows, so I'm literally just going to switch which one is where. So I'm going to put everything in that middle row up top. Everything in that bottom row, so that's now up there in row 1. Everything in that top row now becomes the middle row because we're just switching spots. And I didn't do anything to the bottom. So all we did was just flip-flop these, and row 3 stayed exactly the same. Okay. All right, so let's take a look at the next one. Again, we have a matrix. We want to multiply the first row by 1/2. So we're going to keep the other rows exactly the same. We're only changing that first row, and we're going to multiply every number inside that row by 1/2. So we're going to do 1/2 times row 1. Okay, so half of row 1, half of 2 is 1, half of -4 is -2, half of 6 is 3, and half of -2 is -1. All right, and lastly, we are going to add -2 times the first row of the original matrix to the third row. So we're only doing something to the third row. So let's leave the first and the second alone. We're not doing anything crazy there. 0, 3, -2, -1. It's the third row that something's happening to. So we're doing -2 times the first row plus row 3, and that's what's going to happen to that third row. So I'm going to take -2 times the first row and add it to the third. So I'm going to multiply this number by -2 and then add it to 2. I'll get 0. -2 times 2 is -4 plus 1, so -3. -4 times -2 is 8 plus 5 is 13. -2 times 3 is -6 plus -2 is -8.